Okay, this is module 2 of week 9, and in this module I'm going to discuss Archimedes' principle as a run-up to studying Perrin's experiment. Okay, so what is Archimedes' principle? Well, actually, first of all, what is Perrin's experiment? So Perrin hypothesized that the Brownian motion of a pollen grain should be similar to what we were talking about in Module 1, the distribution of motion of molecules in the atmosphere. And so what he wanted to do is, similar to the barometric formula, he wanted to see that if he put these pollen particles in a jar of water, to see that if, like the atmosphere, there were fewer particles near the surface up at the top and more particles down here near the bottom. Okay. Now the problem with pollen is that if the particles are less dense than the water, then they're going to float all up to the surface, which messes up the experiment. And if the particles are too dense, then they'll actually sink like a stone, literally, to the bottom of the container. That's called sedimentation. So what Perrin did is he figured out a material which was slightly more dense than water, and that was called gamboge, which is tree resin. Okay, and he used this. So obviously he was worried about this buoyancy effect, and we need to discuss the buoyancy effect in order to understand Perrin's experiment. And so this is where Archimedes' principle comes into play. Okay, so Archimedes' principle is that when you place an object in a fluid, it will experience an upwards or buoyant force, and this is the key, equal in magnitude to the weight of the fluid that the object displaced. Okay, so there's two aspects of it. The weight involved in the buoyancy force is the weight of the fluid, okay, and it's proportional to the displaced fluid, the weight of the displaced fluid. So the weight of the particle is rho times its volume v, okay, so the particle has a volume v, times g, that's just mg, okay, so rho is the density of the object. All right. But the buoyant force involves rho F, which is the density of the fluid that surrounds the object. Okay. However, it involves the same V, so it's the volume of the object, because the object, if it's completely submersed in the fluid, displaces its volume. Okay, so rho FV is the mass of the fluid that is displaced. Okay, so in this case, rho FV is equal to rho F and 4/3 pi r cubed in this case, because we're displacing a sphere here, okay? And then G. So we'll do a particular example. Let's say, what's the buoyant force on a wooden ball in water where rho, the density of the wood, is 600 kilograms per cubic meter, and the radius is 5 centimeters, okay? So I can first of all calculate the weight down here. All right. So I take the 600 kilograms per cubic meter, and then I multiply it by 4 pi cubed, and then I have the radius of 5 centimeters, 0.05 cubed, and then I have the 9.8, and that works out to be 600. And then the volume here is 5.24 times 10 to the minus 4 meters, and 9.8. And I calculate that out, and that works out to a weight of 3.08 newtons. Okay, so the object's weight is 3.08 newtons. Similarly, I can calculate now the buoyant force. Now the difference with the buoyant force is that I use the density of the fluid. So the density of the fluid, density of the fluid is the density of water, and the density of water is 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. All right. And so I then plug in 1000, and I use the same volume, the volume of the object here, which is 5.24 times 10 to the minus 4 meters. And I use gravity is 9.8 meters per second squared, and I get a buoyant force of 5.13 newtons pointing up. And so I have a force of 5.13 newtons pointing up, and a force, the weight is 3.08 newtons pointing down. And so the wood will actually rise up in the water until it reaches the surface. So wood floats in water. Okay, let's do this clicker quiz. So previously we used a density of wood which is 600 kilograms per cubic meter, but if I replace the wooden ball with a steel ball, with steel having a density of 7,800 kilograms per cubic meter, how would the forces on the ball actually change? And so the question gives you the gravity force, the weight, and the buoyancy force. Okay. So one thing to do, first of all, is to recognize that 7,800 divided by the original density of 600 is 13. Okay, it's 13 times larger. So the density of the object is now 13 times larger, and that's where this factor of 13 comes from. Okay, this is actually a change in density of the object. Okay. So this will change the weight of the object. So the weight of the object will be 13 times larger, which is all of these. Okay. The question is, what about the buoyancy force? Well, remember, the buoyancy force is rho F Vg, and rho F is the same. It's still water. So because the volume of the object and the density of the fluid remain the same, the buoyancy force actually stays the same. And so the answer in this case is C. Okay? So that gives you some examples of how to actually calculate the buoyancy force. And one question we might have then is, in our barometric equation, we had a gravitational potential energy which just involved rho. So the energy was the mass, rho v, gh, right? And that acted downwards. But now we have an additional buoyancy force. And the question is, how does the buoyancy affect the gravitational potential energy? Well, the answer is that for a particle suspended in a liquid, the gravitational potential energy is going to be reduced by the buoyancy effect. And this comes into the equation as a reduction in the density that appears in the equation for the gravitational potential energy. So it's as if the particle had a reduced mass, okay, in mgh. So rho minus rho L times the volume of the particle times gh is the gravitational potential energy when you're submersed completely in a liquid. Okay? And that corresponds to the fact that there's this additional force acting upwards. All right. So we can use this, or we can use this idea of buoyancy in a couple of problems. So after a night of drinking, you wake up in the morning to find yourself in the middle of Guelph Lake, floating in an oak barrel. The oak barrel has a height of 1 meter, and that's this height from bottom to top, and it's submerged a distance h into the water, and hopefully h is less than 1 meter, otherwise you're going to sink. Okay, so if you weigh 70 kilograms and the barrel has a mass of 40 kilograms, how far above the water level does the upper edge of the barrel sit? So the question asks us, or wants us, to actually calculate this height here. How far above the water level does the upper edge of the barrel sit? All right, so let's put in some numbers here. I'll maybe put it in red. So this height here is total of 1 meter. All right, and the radius here is 0.25 meters. And let's see, you are 70 kilograms, and the barrel here has a mass of 40 kilograms. Okay. So, first way to do this is to draw a free body diagram of the barrel. Okay, so there's you in the barrel. I'll just draw it as a block. Okay, there's a weight acting downwards, which is the mass of you plus the mass of the barrel. Okay, times gravity. And then there is a buoyant force acting upwards. And this buoyant force depends on rho F times the volume of fluid displaced times G. Okay. And in this case, the volume of fluid displaced, if you have a circular barrel, okay, with a height h here below water, it's this little cylinder of height h and radius r, and so the volume here is h times pi r squared. Okay, so I can write this as rho f h pi r squared g. Okay, so this is the volume of this cylinder here. That's how much water has been displaced by the barrel, not including the top, which is not displacing any water, right? This top section doesn't displace any water. Okay, so for equilibrium, if you're just going to sit there, we have the sum of all the forces in the vertical direction must equal 0, and that means then that rho f h pi r squared g going up minus mass of u plus mass of the barrel times g has to equal 0. And then I can solve this for h. H is equal to my plus m barrel. Oh, I can also cancel the g's here on both sides, or in both terms. And so then I divide that, I get rho f pi r squared. And I can write that then as your mass, which is 70 kilograms, barrel's mass, which is 40 kilograms, the density of the fluid, which is 1,000 kilograms, pi is pi, and r squared is 0.25 squared. And if I work that out up here, I get a height which works out to 0.56 meters, which is 56 centimeters. Now, the question asks actually for this little bit, not h, but I do know that the answer is 1 meter minus h. That's what this little bit up here is. This is 1 minus h. So 1 minus h is 0.44 or 44 centimeters. Okay, so the lip of the barrel is 44 centimeters above the water. All right. Let's do this very interesting clicker quiz. So you're shipwrecked and floating in the middle of the ocean on a raft. Okay, so there's your raft. There's you. You're shipwrecked, so you're not happy. Okay, floating on your raft in the middle of the ocean. Your cargo on the raft includes a treasure chest full of gold that you found before your ship sank. So there's actually a treasure chest here. Okay. And it is full of gold. So there's your gold. So, you know, maybe now you're a bit happier. Let's like that. Okay? So you're a little bit happier because you have the gold, but you're floating in the middle of the ocean. All right? So the raft is just barely afloat. Okay? To keep you floating as high as possible in the water, should you leave the treasure chest on top of the raft? So this is this situation. Should you secure the treasure chest to the underside of the raft? Should you hang the treasure chest on a rope attached to the bottom of the raft? okay, hang it in the water? Or should you grab the treasure chest, ditch it, and try to swim off until you find the shore? Okay, so those are your 4 options. So you have to analyze the situation somewhat carefully, and I'll do it here. So I want to look at the before situation, and I want to look at the after situation. And I'll just look at, so the before is that here's the water level, there's your raft, okay? And your raft is displacing a little bit of height here, h, in the water. And there's you, and there's your treasure chest, okay? And so if I look at the forces, if I just look at the raft as an object here, okay, and I look at the forces on the raft, well, there is the gravity, so I'll call it mass of the raft, G, acting down. There is a normal force coming from you, okay, and that normal force will just be your mass times gravity. There is a normal force coming from the chest, and that'll just be the mass of the chest times gravity. And then holding this all up is a buoyancy force, okay? And the buoyancy force will again be the density of the water times the, if this raft has some cross area A, okay, so if it's a flat raft with some area A, then it'll be, well, VG, and V then is the area of the raft times this little height here that you're displacing. So A times H is the volume of water that the raft displaces times G, and that will lead to the buoyancy force, okay? And so equilibrium, again, corresponds to balancing these forces, and so I have rho F AHG is equal to My plus Mr plus Mc all times G. Okay, so that's equilibrium. That allows me to determine the height. Okay, so I want to reduce H. If I reduce H, then that means that the raft lifts out of the water a bit. Okay, and that's a better situation for me to be in. And so for the after, I'm just going to look at one situation, and that is the situation where you have the chest here, mass of the chest, on a rope attached to the underside of the raft, and there you are. Okay. So you can go through the analysis here, looking at the free body diagram of the chest. You have an MCG acting downwards. You have a tension in the rope acting upwards on it, okay? And you have an additional buoyancy force acting upwards, rho F times the volume of the chest times G, okay, acting upwards. And so you must have then that tension plus rho F VCG minus MCG is equal to 0 if the chest is going to be in equilibrium. And that means you can determine the tension in the rope. It's MCG minus rho F, volume of the chest, times G. Okay? And so then I go do this, and then I look at the raft, the free body diagram for the raft. So the free body diagram for the raft, there's still the normal force from you acting down, which is MYG. There's still the mass of the raft acting down, MRG. There is now a tension force coming from the string acting down, which is given by this. And there is a buoyancy force acting up, which is rho F A H prime G. Okay? And now, equating forces, you can see that rho F A H prime G is now equal to MYG plus MRG, okay, plus tension, which is MCG minus rho F VCG, okay? And so comparing these two here for H and here for H primed, because of this term here, the extra buoyancy, because you've placed the chest into the water, because of that, H primed is actually less than H, okay, because this is negative. And so H primed, this This here is what I used to call rho F AHG, and H prime is actually less than H. So it's the extra little bit of buoyancy because of the water displaced by the chest, which is pushing up and allows the raft to actually move up slightly when you put the chest in the water. And so going back to the original question, this will happen either when you do what we just did, or even if you were to secure the chest on the underside of the raft, you displace the same volume of the chest of water, which would lead to the same buoyancy force up. It wouldn't be transmitted by a rope, it would be transmitted by a normal force, okay? So either of these, B or C, is better than A. And I would also say, just argue that D is not very good, because the problem is that when you grab the treasure treft and ditch the raft, your buoyancy force goes way down because your area goes way down, right? One of the things that the raft helps with is it has huge area, which leads to a large buoyancy force, okay? When you jump in, it's just you and the chest, and you'll sink like a guy holding a chest full of gold, okay?